Thank you, Jacob. Let's see if this looks like it works. Hi, everyone. My name is Leo. I work at Powder, where we build tooling to create, accelerate, and secure zkVMs. And today I'm going to talk about compiler optimizations, compiler-based optimizations for zkVMs. Also known as how to accelerate proof generation by 10x without touching the prover at all. Also known as auto precompiles, which is a word that I've been talking about nonstop as of recently. So if you know how zkVMs work inside out, then you'll probably understand most of the talk. But if you don't, I'll try to make it digestible somehow. So usually when people want to improve performance of zkVMs, there's two things that are done. One is just like improve the prover somehow. Different technique, different proof system, different implementations, and so on. The second thing is the arithmetization itself, which is the constraints, how you build the zkVM, and precompiles. So precompiles are handwritten circuits that are used to replace software versions of functionalities you want to use in your guest program, like Ketchak, SCDSA, SHA, and these are examples that are used in Ethereum. But here what we want to do is actually automatically analyze programs and then build circuits automatically that are more optimized than these manual ones so that we get more performance out of that without having to build these circuits manually. And these are the auto precompiles. So what it looks like, I don't expect you all to read this, but this is like some of the RISC-V assembly that's generated from tiny Ketchak when you use it in Rust. It's a lot of instructions. It's actually about 700 instructions to run one Ketchak permutation. So of course it doesn't fit here, but I just wanted to show how large it looks. And when you build a precompile for Ketchak, you actually have one instruction. So you replace that whole thing by a single instruction that now activates a special circuit that didn't exist before that will provide a computation for Ketchak itself. So this should enable a lot of savings. You don't have to understand these numbers, but we're training the software implementation by a specialized implementation. So you have a large circuit that computes Ketchak or verifies Ketchak, but you actually use less data or less computation than before. And this usually provides 5, 10, 30x, whatever, depends on which precompiler you're talking about, speed up in zk-proof performance. And this, of course, makes them essential for guests, especially when you're proving Ethereum, for example. You can get 5x or more improvements in proof generation if you use precompiles versus not using precompiles. The problem is these circuits are very, very complex. So they require a lot of manual labor from expert engineers to develop them and maintain them. It's very, very easy to make mistakes. And if we want to accelerate more and more precompiles to make proofs faster and faster, how many precompiles do we need in the end? What if we end up with tens, hundreds of thousands of these handwritten, super complex, massive circuits? The first thing is it's going to take a long time and a lot of people and a lot of money to develop these. The second thing is they're going to be full of bugs. Enter auto precompiles. So these, it's basically the same thing as precompiles. It's doing the same thing. The goal is the same. You want to get faster proofs by having specialized circuits for things that are complex and expensive to do in software, but you don't want to have a human write it. So these are fully automated processes. So you have the compiler generate all these specialized circuits. It's IS-agnostic, so it's now implemented for RISC-V, but the technique itself doesn't really care what the instruction set is. When the compiler is secured or audited or formally verified, this scales to the circuits that it generates, so you don't have to audit and formally verify and check every single precompile that anyone builds in the world. And the way we write these circuits make them more suitable for form verification based on their simplicity and uniformity. And so we have implemented our auto precompile module inside OpenVM, which is a RISC-V-based general purpose zkVM. And the main experiment here is 25,000 iterations of Ketchak written in Rust. So the first row is the pure software version. So we have some Catch-Chuck program in Rust uses the tiny Catch-Chuck library. We want to make a bunch of Catch-Chuck computations, and there's no precompiles at all. So what happens is we end up with 49 segments. A segment means it's one portion of the whole execution. So if you try to make one zk proof for the whole execution, it would be too big. So it just wouldn't fit in a single zk proof. So you have to break the execution down into several segments so that you can make several proofs for it and then aggregate them together. So the software one actually takes 49 segments. It's a pretty long execution trace. The second row is a manual precompile, which already exists in Plunky 3, in OpenVM, in most, if not all, mainstream zkVMs out there. And if you use the manual precompile, you actually end up with only 4 segments. It's a big, big difference. And you can see that in the proof, it's also a lot faster and gives you a 12x performance gains over just a software version. But if you build an auto precompile for this, we actually end up with fewer segments even, and faster proofs, and almost 13 times faster proofs than the software version. And as reference, when you compare it to the manual precompile, of course, you wouldn't use both at the same time. This is already faster than the manual version, which is, of course, the goal of every compiler, to be faster than things that people write manually. But this is actually, we only got these results. These are updated results from 2 weeks ago. Before that, it was still slightly slower. But after some latest optimizations, the Catch-Chuck auto precompile is now faster than the manual precompile. And this is pretty big results because you don't have to write a single line of code. Of course, you have to write the compiler, but once that's done, it works for Catch-Chuck, ACDSA, for whatever you want to do. Okay, but then how does it work? So when you see all those instructions in the assembly code, each instruction kind of activates a circuit. It can be several different circuits for different instructions, or it can be what's called the CPU circuit, which works for every instruction. It doesn't really matter. It works either way. The first thing you do is collect all the circuits that are used for the assembly block that you want to accelerate. And then we just put them in a giant circuit. So before you had 100 lines of assembly code, each one activates one circuit. Now we have a single instruction that activates a circuit that is 100 times larger. So you traded 100 rows by 100 columns. Nothing changed so far. It will change something in the prover, but theoretically it's the same amount of data. You're doing the same thing. It should be equivalent. But now what we can do is, because you know that all these instructions are in the same circuit, they don't necessarily have to hold the same invariance with respect to memory and communication outside the block. You know they only communicate, some of them only communicate inside the basic block itself, so you can actually inline the instruction arguments and start optimizing the whole thing. What does it mean to optimize the whole thing? There's several things we do. The first thing is the instruction arguments are now constants. They can be inlined inside the constraints, and you can start propagating these values. But one big realization is that the memory is actually, a lot of the memory is local to the basic block. So a lot of the overhead of zkVMs is memory, because each instruction can use registers and memory to communicate with other instructions, and they have to hold invariant that whatever comes in and whatever goes out respects the memory model. The thing is that because we know that a lot of these instructions are local to the basic block, they will not influence, whatever they are writing will not be read after the basic block, only inside the basic block. We don't need these to be memory operations, and it's much better if they are like pure data, or in zkVM terms, or columns. It's much better if they use the primitive data type instead of going through memory, because that adds a lot of overhead that can now be removed. Once the memory operations are removed, now you can remove a lot of constraints that verify the memory operations. You can remove a lot of range checks and remove a lot of constraints, columns, etc. And the whole thing just gets a lot smaller. And so some intuition is that if you have this block of code, you can see that some of the registers are reused a lot. And registers are actually supposed to be cheap in computers, right? But in zkVMs, they're actually implemented in memory most of the time and have the same cost of a memory operation. And so you can see that x14 is used a bunch of times. If you read x14 and you write to x14 and you read x14 again, you're always paying for memory operations if you're just running this as software. But if you realize this and you actually connect all of these things as a circuit, instead of just always going through memory, you can actually remove a lot of memory operations. And some intuition on constraint solving, which is actually the heavy lifting of this whole thing, because we realize all this high-level semantic information on what is a memory operation, it's expensive, how do we remove memory operations, and all of this, we call it high level because you know the semantics of memory and so on, but the zk circuits, they're actually written as polynomial constraints that kind of look like this. They're very simple constraints that only use multiplication and addition over a prime field, and the more columns you can remove from these constraints without causing bugs, basically, the more efficient your system will be. So in this case, this is one example of what shows up when you call any of these instructions, add, sub, XOR, or AND, in this specific implementation. They are all implemented in the same chip, in the same circuit. So you have one circuit that actually implements all of these instructions. And there are these flags to select which instruction is running, and this is what the constraints look like. And there's not much you can do here. But we know that when we build the auto precompile, the opcode, we know the opcode because we know what the assembly code is. So let's say the opcode is 414. In this case, there are things you can infer. And actually, I don't know if the slides got updated last minute, but so when we have this system of constraints, this set of variables, there's only one solution. So I'll give you 10 seconds to give me the solution. Except for Chris. Exactly. Why is that? He just solved the constraints, fair enough. But yeah, this is what happens. So all of them are Boolean. So you know there's 0 or 1, right? And you know that their sum has to be 1, meaning one of them will be 1 always. You don't know which one, but you know only one of them will be 1, and the rest will be 0. When you have only these options, and you apply them to the last constraint, you know that you can take the 512, move to the other side, you end up with 2. So 2 equals the rest of the thing. Because of the multiplication by the constants, there's only one option that fits this, which is XOR must be 1, the other variables must be 0. That is literally the only way you can satisfy this constraint. The constraint has to be satisfiable, otherwise the zk proof will not go through. And this is the solution we end up with. And this is also pretty powerful because now that we know at compile time, which is the important part here, we know at compile time that these are the values. If we know them at compile time, we don't need any of them. We can just inline all of these values, remove all the columns, remove the constraints, and this is how we start accelerating the chip. So basically just removing stuff, and this is still sound. We did not introduce a bug here. When this instruction is applied over a certain set of instruction arguments, it will lead to this valuation of the variables that is all the compile time, and you can remove a lot more things. This is one of the simple cases. There are a lot more complex constraints that are solved, but this is basically what the heavy lifting is that allows us to actually remove a lot from the circuits, as we'll see later. Well, we'll see it now, actually. So when we do the first step, which is taking the circuit for each instruction and putting it in a massive circuit that is not optimized, but has the same functionality as the original assembly program, the upper part of the slide is what you see, that is the size of the circuit. So for Ketchak, when we take the assembly code that computes Ketchak, simply inline all the circuits, no optimizations at all, we end up with 20,000 columns, 25,000 constraints, and 13,000 buzz interactions, which is a type of constraint, but different from polynomial constraints. And they also end up introducing more columns later. And columns affects the proof generation, but especially for recursion, more columns is pretty bad. So that's why we want to minimize the whole thing. So after we apply all those optimizations that I mentioned before, memory, constraint solving, et cetera, we end up with less than 2,000 columns, so less than 10%, only 161 constraints, which was almost nothing, and 1,700 buzz interactions, which is a bit more than 10%. So you can see that the optimizations are actually very, very heavy in the sense that there is a lot of there's a lot of overhead that the memory and other things have on the assembly program that we can actually remove once we make a circuit for it. Yeah, so this is what we've done so far, and there's more to do. So there's always more optimizations you can make. There's more constraints you can solve, and there are two things we're looking into called array stacking and Planck circuits, which solve one problem that comes up later. So when you change these circuits to make proofs, the first layer of proofs, so what you saw in segments earlier, you get one proof for each segment. And for these, it doesn't matter too much whether you have more columns and more, whether you trade columns by rows and different things in the circuit. But once you do what's called the recursion tree, because you want to end up with a single proof in the end, it matters a lot how many columns you have and how many circuits you have. So you actually want to reduce the number of columns because of recursion, and array stacking and Planck circuits are attempts at solving the performance issues that show up once you do recursion. Another thing we already do is always trying to come up with smarter ways to detect basic blocks. So you're only given an assembly program. How do you know which basic blocks to accelerate? Currently, we do profile guided optimizations, which is we run a few sample inputs over the program and then kind of analyze which basic blocks are more expensive, which run more, how many instructions does it have. If we make a chip for it, what's its effect in the final proof with some metrics of the size of the chip. But if you have smarter approaches to compute this, then hopefully the end result is even better. One thing we haven't started yet, but is as important as the whole thing, is formally verifying this, because obviously we're taking a bunch of circuits and we're giving back a circuit, and if the original circuits were audited, what happens to the new circuit that the compiler generated? How do you know that it does the same thing? How do you know it didn't introduce bugs? So there are a few things you can do. You can verify the compiler itself, verify the techniques. You can apply compiler validation and try to prove that the generated circuit has the same semantics as whatever you had before. There are different things you can do. But we think these circuits are quite amenable to form verification because they're actually quite uniform and quite simple. And on the benchmarking side, we are doing more comparisons similar to the Ketchak one with different chips to use as reference and see what else can be optimized, and also trying to provide acceleration for Ethereum benchmarks without having to change the prover at all. That's it. Thank you.
All right, thank you very much. We have a couple of questions, and I think we have to share a microphone. First one, why auto precompile instead of just optimizing every program?
Oh, the second question. Why auto precompile instead of just optimizing every program? I'm not sure I fully got the question, because it is what it does. So you can take any program. I don't know if you meant the entire program, like the first question. Maybe I can answer both at the same time. So this is one of the ideas. So you can theoretically take every single basic block of the whole program, make one circuit for each one of them, and then just allow the prover to choose whether they want the software version of a basic block or the accelerated version. There are implementation details about this that make it difficult. So right now we only do it for selected basic blocks. But any input program can be accelerated like that. So it's not only Ketchak, and there's no manual implementation. You can do it for any program. I'm not sure if that answers the question. I'll just go through. Yeah. So will these optimizations become part of the OpenVM toolchain? So currently they are implemented at a different repo, but because of the OpenVM architecture, you can actually add extensions without changing OpenVM at all. So you can use like the official OpenVM repo and then also use the powder extensions on top without having to change anything. So ideally, we had to make a few changes to OpenVM, which we didn't want to do to preserve more compatibility. but this should be possible to upstream, and yeah, hopefully they can become like part of the official code, OpenVM code base as well. The integration, I mean. How does form verification tie in? Yeah, so the idea is that basically, I mean, the single goal is that you don't want the generated auto precompile to be buggy. So that's basically what you want. And how to ensure that, there's different ways that provide more or less assurance. If you verify the generation itself, you formally verify that, or the approaches, that's one thing. But that can also be buggy, right? So the verification can also be buggy. And ideally, you also want to have something that can analyze each generated auto precompile and compare it to the original assembly code. And hopefully, if you stack all of this together, you get more assurance over the final circuit not having a bug. So you can, there's several things you can do. Length of the program that had a catch-up and gave 3 segments for auto precompiles. If it's short, oh. So I answered the second one just now. How much work would form verification for the compiler demand? Probably quite a bit. But it has the advantage that if it's easy to say, but like if you do it once, it's done in a way, which obviously not true because it will keep changing and you have to keep updating. But it's effort that scales, right? So if you don't have that, then you have to audit every single precompiler anyone ever writes for guest programs for different use cases. But if you verify the compiler, which is obviously is a lot of work, at least that scales to anything that you build with it in the future. What was the length of the program that had a catch-up and gave 3 segments for auto precompiles? And if it's short, is that an indication of the increase in performance for full VM execution? I don't know exactly the length of the entire trace, but 49 segments in software, you can sort of assume roughly 1 million cycles per segment. So a little bit more depending on which instructions, which chips are used. So about 50 million, I would guess. So it's not short, but it's also not like EVM block verification. And yeah, so we have run initial benchmarks on EVM, like Ethereum block verification, in the presence of manual auto precompiles, which is the state right now. We want to advance the state as is. There's 2 things we want to do. Experiment on Ethereum block verification with all the precompiles that already exist and without any, right? It's because if auto precompiles are even better than the manual ones, it might make sense to not even try to use the manual ones and just go straight to accelerating the software version. We have not done that yet. We did run initial benchmarks on block verification with manual precompiles present, and we see about a 2x improvement at this point in very early experiments. Is it always the case that you have linear constraints optimizer? Good question. No, there's also quadratic and probably even cubic constraints. Chris, just say thumbs up or thumbs down. Okay, thumbs middle. So quadratic for sure. Cubic, I don't fully remember, but yeah. How complex are these compiler changes? Lines of code, months of work. So it's been a couple of months of work, but from scratch and a lot of experimentation, a lot of refactoring. We first implemented it for powdrVM, but then for OpenVM, a lot of integration work. In the end, it's not that much code, actually. So if I had to guess, let's say 4,000 lines of code. I don't know. Does that make sense? We have people from the team in the audience, so I just keep asking them. Thumbs down, thumbs up, thumbs up. So 4,000, let's go with 4,000. Thank you.